an Abby's class after this.
Yeah, I am. There, it's a toss up. I'm gonna let them decide whether they want me to continue on or just fuck around for the day. I'm gonna ask them, like, would you rather hear about what I do? Like, this will be your first time talking to an actual PhD level chemist. Maybe there's something you're curious about.
Yes, that's from what I know, from what Abby said, they're already way ahead anyways.
That's right. I think she's about half the lecture ahead. So, like, I was thinking about spending half a lecture just kind of doing Q&A. And then
Fucking around.
yeah, and then maybe I'll do some. God, we're doing titrations and buffers, so like it's not exactly the most engaging material in the world. And not to say that I'd rather just have Abby do all the painful stuff, but
Then again, how invested do you think a group of Gen Chem students will be in actual?
actual chemistry.
Yeah.
Well, that's my. I don't know. So you're right. That's a very good question to ask, and I don't know the answer. That's why I'm gonna be like, would you rather hear about some
They'd
actual
rather,
chemistry, or would you rather just trudge along? You know,
they'd rather do it so it's stuff they don't have to take notes on.
that's what I think.
I don't think
So,
they'd rather do it because they're interested.
I'm gonna be optimistic about it.
But it'll.
There's got to be at least one person in there who's interested in chemistry.
And all the forensics people in there who will have to take DChem. Well, at least they'll be.
That's right.
Yeah. Right spec delivery get here yet?
I have not heard. It's either today or tomorrow. I need to actually go make sure there's room for it.
It's just going down on a loading bay, right?
Yeah, but there's always crap down there. I just gotta make sure there's. Yeah, I agree. I don't think it's an issue. I just haven't looked.
Because I like over, I think I like over and it was dry. It was a way worse, yeah, but it was kind of crazy. That was crazy. So like you gotta reach out and really try to put down. No, I don't think when I walk. But I was like, I'm sorry, I walk out of the it was bad. It was sad.
Yeah. The forensics lab that Logan got a position at had an opening for basically being in their stock room.
Okay,
That's
that sounds kind of boring.
managing ship.
Yeah.
And
You're better than that. Don't apply for that.
yeah, I am probably better than that.
You're gonna apply for it anyway, though.
No, I did. I
Oh,
applied
okay.
on Thursday as another test of the
Right,
this is the company I think just has me muted on Indeed. So I'm definitely very qualified.
that
with
is
They'd be muted on
it.
Indeed.
And I've heard shit, even though I messaged them.
I hate when companies aren't communicative.
Yeah, when Logan applied to them, he I scheduled an interview like 6 hours after he sent the application.
Jesus, that's crazy.
Yeah, and that's, I have a friend who graduated last year who went through the same thing. She heard back like instantaneously.
Yeah.
HR is usually on it.
Yeah.
And they just have ghosted me for like 2 weeks.
Yeah, that sucks.
But I found their HR's LinkedIn page and I'm probably gonna send some message.
Okay, cool. Well,
Like,
good luck.
Yeah.
Which lab? About the dive lab and like, yeah. And I was like, oh, we should go in the lab tonight and like, oh, the data analysis. I was like, oh, that's a great idea. That was just my dream. I was like, I'm pretty much. I have a lot of movies.
That's not this.
I know, but this is the last week of teaching class, so if you want help, like, you have to go on this week, you can't help, like, yeah.
I mean,
Y'all want me to go with, I was in, I don't know. Oh, and one of them didn't work because it was giving us the law school, or the green one. It was giving us a weird, the reading that I got in was like a yellow reading, but I really was. So it's just not, so, yeah, you know, bad in the solution will start. Like when you start, it's so on, okay, it was not. My provision is small. I think one thing, I think it was, okay, go ahead. No, it's never done. Or did, I have not. Her analysis of figures.
Yeah, and I'm gonna write a paper and be like, you know. Be like, I'm sick, I'm sick right now. This thing was definitely like.
What kind of?
I do like visualization. It's used to that. I think any footprints and stuff, but like the legalization.
In the morning, yeah. And we have had it in. Yeah. I go to next week on the 15th, but I think for that, I think they'll go. Section. I would. Even this. From my. Oh, I was actually watching. Last night, after yeah, I know. I was out here for live. Yeah, no. We got a lot. That's not. What's weird, you know, it's like my. I think it's so bad. When the first, you know, like mine didn't.
No, don't print, don't print. Huh?
Hello, you ready to teach Gen Chem 2 today?
Sort of. I'm gonna give them the opportunity to not I'm gonna give the students the opportunity to get me off on a tangent today. So I'm just gonna ask them, like, this is your first time probably in front of a PhD level chemist. Was there something you'd like to learn that you're not learning that I could teach you? And so we might just go off on a tangent today. Let's see how it goes. Otherwise, we're doing buffers, much to my chagrin. Buffers are boring.
Offensive, like, yeah, like, just a little bit. That's why I was like, I'm trying to.
Okay.
Right.
Before we get started, I just want to say something real quick. Exams will be returned to you tomorrow via campus. I've graded this section already. I wanted to return everything in one go, so I'm almost done section 2. Which has taken a little longer than section 1. You guys did pretty well on it, I thought. If you want to know your grade on the exam today, and your current letter grade, send me an email.
You can also ask me at the end of class, but I gotta run because I actually have to teach Gen Chem today for somebody. I know, right? So I'm gonna try to convince them to have me talk about something other than what they're learning, which are buffers, which I hate. Yeah, exactly. That's exactly how I feel about buffers. Yeah, yeah.
You can start talking about each other, scare the shit out.
I might.
Good.
I might.
Oh, yes.
What was that?
Dry Pittsburgh.
Dry Pivnert?
Yeah.
Yeah, that sounds good to me. I was gonna ask them, because up to this point, they've only ever had adjuncts. So like maybe they've got some questions about chemistry that they've thought about, but no one's ever answered for them. And I thought maybe I could give them answers to those questions. I mentioned that to Sean, and Sean said, well, that's assuming that they care, which is about that. So I'm hoping there's a couple interested chemists. So yeah, just send me an email today if you want to see your grade today, or catch me immediately after class because I gotta leave. Okay, so we got maybe 2 lectures left. Actually, we might only have 1 lecture left in atoms. No, I'm gonna say that we're gonna finish up atoms this week. So we got 2 more lectures. We're running a little slow, but that's okay. I think this is an important topic. And this lecture today is one of my favorites. So again, as I promised last class, we're starting to move away a little bit from integrals. We have these magical atomic orbitals that kind of more or less, in terms of wave functions, they don't really change that much from atom to atom. One of the s orbitals kind of always look the same. We'll talk next class. Next class actually we'll talk about multi-electron atoms, helium, and so on. We'll look at trends. We're gonna really dig deep into atoms. Of course, we could spend an entire year talking about atoms doing them all. So I want to finish up hydrogen today. We're gonna talk about the energy levels of hydrogen, and something that's interesting that we'll see very quickly. In fact, the experimentalists saw this early on before they even understood why. That this idea that energy levels are kind of like, we can call this a 1s electron or a 2p electron in our atom, not really a meaningful approximation. Well, it's an approximation. Let's put it that way. It's a meaningful approximation, but it's not precise. But the idea of an orbital giving you some information about the character of the electron only works so much. And the problem, the wrench that we throw into the cogs of our Schrodinger equation for these orbitals, that's going to fudge everything up a little bit, is spin. All right, we really haven't talked about spin at all. We know it exists. Today we're going to see how it affects the hydrogen atom specifically. That's actually quite interesting. Before I do that, though, we should talk
just briefly. I can't remember. I don't think I really got into this last class, so I'm going to kind of go through it. The raw energy levels of the hydrogen atom. Right, we've looked at the orbitals in good detail, I would say. Of course, we are looking at P's and S's. These are just hard to draw, so I don't often talk about them. The question, of course, are what are the energies of electrons in these orbitals? We haven't discussed yet. And we've noticed that there are these, structures in terms of angular minimum, right? Or just in general, we have 1s, 2s, 3s, where we have the n number. We also have angular minimum, right? And it's a question, of course, whether the energy is, what's the energy dependent on? Is it dependent on the angular minimum? Is it dependent on the orbital radius, which it should be? And what we're going to see is that all of those angular minimum effects that we've been talking about kind of average out in the hydrogen atom. And that's actually a really beautiful result, and I'll talk about the consequences of it. But the equation for the energy for the hydrogen atom, I think if you go back to the first lecture we talked about, I talked a little bit, or maybe it's the second, we talked about the spectrum of hydrogen. And we talked about the different people who observed it way before all of this theory was invented. And I showed you these patterns that you see in the absorption or the emission spectrum of, say, the hydrogen atom. And I said that the scientists who studied these before all the physics was developed, numerology effectively, they fit their equation to a formula for these patterns. And let me again just show you a picture of a pattern here. I don't think I can copy paste into my document anyway. But anyway, this is kind of what the excuse me, sorry. This is kind of what the visible spectrum of the most intense peaks of hydrogen look like. All right, so our wavelengths here are in angstroms, not nanometers. So this is 120 nanometers. So you just divide by 10 down to 90 nanometers. So this is in the ultraviolet. And you see in the ultraviolet the series of lines. This is called the Lyman series. I'll go back to what this means in a second. And it's named after Lyman, who was the one who first kind of characterized this formula, this structure. And Lyman sees the series of lines that ultimately go to a limit, right? They get closer and closer together, right? And then the lines disappear at some point, which is at 912 angstroms or 91.2 nanometers. Right? So he sees this pattern for hydrogen gas with this progression that converges to basically the gap between each line goes to zero. Okay, so he sees this, and I'll show you later that if you go longer in wavelength into the red, there's another pattern that looks like this as well. There's many patterns that look like this, but they have this very similar pattern that look like this. I want to talk a little bit about this pattern today. And then we're gonna throw a wrench into this pattern even more, as you'll see in a second. So the way that Lyman and Balmer and all these old guys come up with is that they show that the formula for the Lyman series or the wavelengths of the Lyman emissions or absorptions, whichever you prefer, of hydrogen, follow this formula. 1 over lambda, which again is the wave number, right? That's energy. 1 over the wavelength, which has units of inverse length. You could put it in wave numbers if you wanted, is equal to this constant R sub h. This is an experimentally determined number, or it was at the time. This is just an experimental parameter. And what Lyman and Balmer and all these old guys realize is that the formula can be determined by one number, n. Okay, so it says that every one of these lines in the spectrum, we call each of those peaks as they converge, that the energy or the wave number or the wavelength, let's just stick a wave number, 1 over lambda, the energy that you observe where the absorption or the emission is equal to some number which has units of energy, inverse wavelength, times 1 minus 1 over n squared, where n is a number. Right? And the way that Lyman did this was very simple. Let me just go back to the formula one more time, the picture. Right? He said that this is n equals 2, n equals 3, 4, 5, 6, 7, 8, 9, and so on. Right? So he said this is n equals 2, n equals 3, right? And he just lines them up and fits it to a line. And he just does a linear regression on this problem and finds that this pattern fits perfectly to very, very high precision, certainly up to the precision of their experiment, to this formula. Right, so here N has to be, I'll just write this for the Lyman lines. N in this case is 2, 3, ... Okay, so he notices that the pattern of the lines gets smaller and smaller. Basically, the differences scale is 1 over n squared. Right, that's why they converge to this limit. Right, and if we take n to go to infinity, right, this term goes away. You get 1 minus 0. So the energy of the state at n infinity, which is the limit of this progression, is at r sub h. Right, this number. Okay, and he fits this number. Lyman fits this number, and I think it's actually Balmer that does this. I can't remember. He fits it to about 1.0968 times 10 to the 7 inverse meters, right? Which is about 109 nanometers. Let me think about that for a second. Yeah, it's about 90 nanometers in wavelength. This is in 1 over wavelength energy. All right. Now, and it's actually, if we look at the spectrum, I'm just going to go back really quickly and I'll come back. That the limit is at 912, 91.2 angstrom, 91.2 nanometers, right? This is the value R sub H, right? It's the limit highest energy of a transition for this hydrogen progression. So he finds this and it fits beautifully, right? He gets like a shocking amount of significant digits on his estimate. He gets 5 or something like that, which is very impressive. This is like 1840, 1850. Okay, so, but the thing about Lyman and all these guys is that they don't actually understand what's going on. This is pure numerology. He's taking a spectrum and fitting it to a model, and that model has no physical meaning. He's just fitting a best fit function to it. And so Lyman sees that this works beautifully. But he doesn't really understand what's going on, other than it works. And Lyman and Balmer and all the other guys that study atoms, atomic spectrum, really hot topic around 1870, 1880. They look at other atoms besides hydrogen, other regions of the electromagnetic spectrum as well, and different atoms. And they find that these patterns are pretty similar, but the value changes. So the limit changes for each of these patterns. But in general, even for complicated atoms, sodium, whatever they could pull into the system, all of the atoms have very similar patterns, but each one has a different pattern. All right, and unfortunately for him, this formula doesn't work. This formula only works for hydrogen. Right? He sees I'll look at some spectra next class of more complicated atoms. You'll see that they have these patterns that look a lot like hydrogen, but they look a little funky. They still have the same kind of patterns, right? There's obviously some structure to the absorptions, but it doesn't follow the same pattern as hydrogen. All right, so Rydberg and all these guys, or not Rydberg, sorry, Lyman and all these old astronomers and spectroscopists, they're really lost. We understand hydrogen perfectly, but once we get to helium, all hell breaks loose. But they understand that there's these patterns, they just don't have any physical theory to explain the patterns. They can only do it for hydrogen. And it turns out that their answer for hydrogen is precisely correct, but just coincidentally. Just coincidentally that they got the right answer for the wrong reasons. So the question, of course, is what's the right answer for the right reasons for this formula? And well, we solved the Schrodinger equation for the hydrogen atom already. Right? We know all the wave functions. We know the Hamiltonian. We can calculate the energies. So we can get them exactly. Right? And so what do we get exactly from theory? So from our quantum mechanics, what do we end up getting? Well, we find that the energy is only dependent on one number, n, principal quantum number. Right? Notice that there aren't, in Lyman's formula, there's not 2 parameters. There's no L, right? There's only n. But that should tell you something, that there's no angular momentum dependence. There's only dependence on one number, one parameter. But there are 3 parameters in hydrogen, right? There's n, L, and m sub L. that tell you the state, but the energy only depends on the principal quantum number. And the actual formula for the energy looks very complicated. It's got a bunch of it's got a bunch of numbers in it. So I'll go ahead and write it now. So it's the energy is equal to the charge of the electron squared divided by 8 pi squared epsilon naught, that's the permittivity of free space, the conductivity of the vacuum, times the Bohr radius, times 1 over n squared. Right, so the energies of all the levels have no dependence on the angular momentum. Basically, Bohr's model of the hydrogen atom, this idea of concentric orbits of the electron around the atom, well, in terms of the spectroscopy in the 1900s, that was perfectly valid, right? They saw a spectrum consistent with a set of concentric orbits whose distance from the proton is proportional to n. And the energy goes as 1 over n squared. Okay, so of course there's some funky things here, right? What is this value for and remember, n can be 1, it can't be 0, and 1 is the minimum number, right? The 1s orbital. Right? You get a negative number, a negative energy for n equals 1. Right? So we'll have to think about that way that the energy levels are constructed in terms of energies in just a second. But when you, right, the important thing here is that this whole number right here, all this crap right here, it's just a number, it's just constants, right? A naught is dependent, as we talked about on the speed of light and Planck's constant, right, has all this relationship to the physical constants. And so this is the physical this is basically dependent on C and H, all the constants we know and love. And there's also some electrostatic units on there. We got to account for the charge. That's just a number. And the units of it are energy. Right? And so the units of this thing that I'm about to circle in green have joules. Those units of joules. Okay, and so we can multiply. You guys probably saw this on the homework on the exam. If you have a unit in joules, a value in joules, you can get it in inverse wave numbers by multiplying by the Planck's constant times the speed of light. So we can take this thing and multiply it by hc, and this will give us units of inverse meters. This gives us inverse meters, right? And the value that you get once you put all this together and evaluate it is 1.9678 times 10 to the 7 meters, inverse meters. Right? It's exactly the same as what Lyman got 100 years before. All right, so Lyman got the right answer. You better, if you fit it to a really simple formula and it fits beautifully, it better be right. But what he determined was the correct prefactor on the energy, if you will. The thing that determines the energy levels of hydrogen is this big number, where they lie, and he got it right. He didn't realize this at all. But I think the important thing to think about now is that the energies of the orbitals are only dependent on n. What does that mean? Well, that means that in the n equals 2 state, right, you have 2s and 2p's, they all have the same energy. Then you go up to 3, the 3s, the 3p's, and the 3d's, they all have same energy. They're all degenerate. So there's really no preference in terms of energy, as far as we know, from here, there's no preference for the electron and hydrogen to be in the 2s or the 2p. Doesn't matter. It only depends on n, right? The size of the orbit, right? That's the thing that Bohr thought about, right? Bohr says that the height, right? He only knew this issue, right? He saw that there's this formula for the energies, and he hypothesized that the way to get this is to assume that the electron orbits the proton like a planet. Planetary type model for the atom. And so that would mean that, again, the energy of the orbit only depends on the distance, right? That's what Kepler tells us about orbits. So this makes a lot of sense in that regard, right? So the question, of course, is where does angular minimum come into play? It seems like we talk about angular minimum all this time and it all disappears, like it doesn't matter. Of course, we know it does matter because we have atoms like carbon and oxygen that have valence electrons in the p orbitals, and that has very, very, very important consequences on bonding. We know that there's some distinction in atoms between p and s orbitals and d orbitals in atoms with many electrons, right? Talk more about that next class. But in the hydrogen atom, it doesn't matter. 2s to 2p's are all the same energy, as far as we can tell. Right, so of course, to get to the formula that Lyman comes up with, Lyman measures differences in energy between states. So he's calculating differences of this number between two different values of n. Right, there's that. So right, you have a sum, right? You have this number r sub h. This is r sub h right here. And he's subtracting 1 over n squared from 1. Right? A better way to write this, of course, this 1, just to kind of give it away, it's better to write this as 1 over 1 squared. Right? So these are the energies of the absorptions starting from the n equals 1 state, the 1s orbital. Right? So the Lyman pattern that I showed you, this one that's at high energy, let me just take a picture one more time. These are the transitions starting from the 1s orbital and going up to the higher states. So the Lyman alpha line, which is the name for it, if you've ever done solar photography, Lyman alpha is the most common way to study hydrogen in astronomy. They have literal filters for cameras that only pull out this frequency, this wavelength. And you can study astronomy this way because it's a great carrier for hydrogen. Very bright. Right, so this is the n equals 1 to n equals 2 transition. This is taking the electron from 1s to 2s or 2p. We don't know. We'll have to look at that. And this would be the from 1 to 3, 1 to 4, 1 to 5, 1 to 6. And then it just keeps going and the spacing gets smaller and smaller because it goes as 1 over n squared. And eventually what happens is the lines disappear at 912 angstroms. Now what would be happening there? Well, the fact of the matter is that we've pumped so much energy into this electron that we've kicked it out. Right? Just like in the iodine lab, you may have noticed that in your spectrum as a function of wavelength, you have sharp lines, sharp lines, sharp lines, and then suddenly you just have this broad hump that just dissipates. You don't have the sharp lines anymore. Right? And what was the interpretation in iodine? That was you put enough energy into the molecule that's disassociated into the atoms. Precisely the same thing here. Pumping more energy into the hydrogen atom, exciting that electron to the point where you put in so much energy that it leaves. You ionize the atom. So there's no more hydrogen to excite anymore. You just have a proton and an electron. It doesn't have any absorption anymore. And this, at this point, is the exact ionization energy of hydrogen. Direct measurement of it. So let's kind of put this together a little bit and think about the different levels of hydrogen and what the energy level structure looks like, right? So let's take this spectroscopic data and our energy formula and start building patterns of levels, see what the level structure looks like. Okay. So let me just go ahead and write that formula again. So we have that the energy, the nth state. Now is going to be this constant r sub h over n squared minus, and r sub h has a special name. It's called the Rydberg constant, named after the man who discovered it, the actual version of it, Mr. Rydberg. All right. And n can be anything between 1 and infinity. And so let's come up with so I wrote down a value for the Rydberg constant. It says 1 times 10 to the 7 inverse meters. That's not a very useful number to use. So let's use a different unit. Right, and the unit I'm going to use for this is electron volts minus, and so the Rydberg constant is exactly, or roughly, let me write roughly, 13.6 electron volts. All right, and I'm just going to say electron volts are going to be a convenient unit for us because it's, right, this is, as we see, the energy, the state is 13.6 eV divided by 2. So we take n to infinity, which would be we ionize the atom. It takes 13.6 eV to do that. All right, so this is the ionization energy of hydrogen. So we know for a fact if we put in 13.6 EV of energy into hydrogen, it just disassociates into, and well, it ionizes rather. All right, and if you want a comparison, an EV, the 1 EV is about 90 kilojoules per mole. All right, this is a useful unit to use when you're dealing with electrons because a bond, right? Well, an ionization energy is on the order of 10 EV, at least for hydrogen. A bond's on the order of 3 or 4 EVs, kind of on the order of 1 or 2 EVs, kind of a small number. So it's kind of a convenient number to use for electrons. Right? Most bonds are around, if you remember in the exam, the bond strength of OH is about 40,000 wave numbers. It's about 500 kilojoules per mole. It's about 4 EV, 4 or 5 EV. Right? That's a typical bond. Right? It's a useful unit for bonds and electrons. Okay, so let's look at what the energy level structure looks like this for this. All right, so all we're going to do is we're just going to plug in N and calculate the energy. All right, so let's go ahead and do N equals 1. I'm going to put it at the bottom, right, because the energy formula is negative. Okay, so the N equals 1 is at an energy of 13.6 EV. Right, and let's do the other limit, which is N infinity, right? We know what the maximum energy is going to be. It's going to be N infinity, and that's going to be 0, right? So the ionization energy at infinity on this scale is 0 EV. Okay, so the reason why we use a negative scale here is exactly why we precisely the reason why in the Morse potential when we plot it, that the minimum is typically below E equals 0, right? We assume E equals 0 is the disassociation limit, and everything below that is attractive and bound, right? So every level up to the ionization limit is a bound, stable state, right? 0 EV is the limit of stability. Once you put in that much energy, more energy than that, you've broken the atom into 2 pieces. So we use a negative, for atoms, we typically use a negative scale, but we can also flip it so that this is 0 and this is 13.6, right? Doesn't matter how you do it. It's just arbitrary. Okay, so let's go to N equals 2 now, right? Where does the next level show up? Well, it's going to be at 1/4 of the Rydberg constant, right? We actually jump up quite a bit in energy. So N equals 2, we'll just kind of write it here, is going to be at 1/4 of 13.6. So this is at minus 3.4 EV. Okay, and let's just look at the transition between these two, right? The N equals 1, the N equals 2 transition. This has an energy, a delta E, of about 10 EV. Well, it's 10.2. Right, and this is the transition between the N equals 2 and the N equals 1 state. This is what's called the Lyman alpha transition, right? Which is that line that I showed you in the spectrum. Let me just go back one more time. Right, it's this line right here. Bless you. Right, so it's at 121.6 nanometers. So this is at 121.6 nanometers. Okay, it's a really classic example, right? This is the fingerprint, the classic fingerprint of hydrogen, the Lyman alpha. All right, and so now let's go to the next level, but the gap between n equals 2 and n equals 3 is not going to be as much as the gap between n equals 1 and n equals 2. Right? Because the difference in the fractions is 1 over 4, and here the difference is going to be 1 over 4 and 1 over 9, right? Which is, of course, a smaller number. So the gap is going to start closing. Let's see if I can do it on the right scale. Like that. So it's at minus 1.51 EV. And then we just keep going, right? And the gaps keep getting smaller and smaller because they scale as 1 over n squared. Right? So 4 is going to be a little closer. It's at minus 0.85 EV. And then I'll just continue on, right? The 5 is going to be even close. Oh, let me get a different color. The 5 is going to be even closer than that. 6 is even closer to that. 7 is even closer to that. Right, and eventually the lines just basically blur together as you go to the infinity line, as you go to the ionization limit, right? There's many, many, many states of hydrogen that lie right below the ionization. And I'll just write 5. 5 is at minus 0.54 eV. And it just keeps going, right? People have measured hydrogen in states where n is equal to 100, 95, 120, right? This is where the electron is basically where Pluto is, or even further than that, right? It's super, super far away, right? Remember the distance between the electron and the proton in the 1s orbital is about half an angstrom. That's about an angstrom. Okay, let's just say an angstrom, right? By the time you get to n equals 100, it's a nanometer away, right? It's a factor of 100. Even 1,000 times further away, right? So you've got this giant orbit of this electron around the proton, and it's a perfectly stable molecule. Now, if the molecule is like right here, and we sneeze on it, we might inject enough energy into it to ionize it. And so, for instance, if you can prepare an atom in one of these really high energy states, the name for these are called Rydberg molecule atoms. Not important. You only need a very, very low energy light source to ionize it, right? Because the gap between this level and the ionization limit is very, very small. And so when you're at n equals 100 or 110, you don't need a visible photon or a UV photon to excite it and ionize it. You just need microwave radiation, maybe an infrared photon, right? Very, very low energy. Right, so there's lots of really, really cool effects with these atoms, these super excited atoms, because you've got these giant orbits. They have huge dipole moments because the proton and the electron are really, really far apart. They're super polar, super big orbits, and they have really, really funky behavior. And you can do cool things with them using light that is much, much, much longer wavelength than visible. There's a whole field of physics and chemistry that studies these systems. You can do it with molecules and atoms, psych them right to the limit of the ionization. All sorts of crazy things happen up there. But I've only shown one transition here, but as you can imagine, there are any number of transitions between the levels, right? Not just from 1, but it could be from 2 as well. Right, so there's going to be a series of levels that all start from n equals 1 to n equals something, right, which are written in green. Right, so the green ones are called the Lyman series, which are all the levels, all the transitions that start at n double prime equals 1, initial state. Okay, and I showed you a picture of them, right? Most of the Lyman lines are in the ultraviolet. So that the spectrum. But you can imagine that I can start at n equals 2 instead. Right, and I can have a series of lines that are longer wavelength or lower energy that connect N equals 2 to all the levels above it. Right? This is what's called the Balmer series. And this is in the green. I should have written it as a green.
But these all start at N double prime equals 2.
Supposed to be like quotations around, say it says Lyman series colon, and what is that supposed to be double prime?
Where do you see that?
It's
Here?
yeah,
Yeah, N double prime, the initial
Oh.
state. Yeah. Right, so it's all Lyman series, all the levels that start at N equals 1. Balmer series, all the ones that start at N equals 2. These are, so I'll just write really quickly that the Lyman series again are in the ultraviolet. The Balmer series is around 600 nanometers in the green. All right, if you excite tube of hydrogen,
You don't see the Lyman lines because they're ultraviolet. You see the Balmer lines
predominantly. They're kind of greenish. Actually, I think they're kind of greenish red. Depends. I forget exactly. And then, of course, there is a series of famous lines that start from N equals 3. And these are in the infrared. These are called the Paschen series. Again, they're all named after their discoverers. None of these three guys know anything about quantum mechanics. They're just people that take light, shine it at an atom, and then look at what's absorbed. This is all numerology. This is in the near infrared. So when you excite hydrogen, maybe I'll find a picture of it just a sec. So when we excite hydrogen and do a hydrogen glow. Oh, so it's actually purple. So when you take a spectrum, when you do a discharge of hydrogen, you get this beautiful purple color, which is coming from the Balmer series of the system.
primarily the Balmer emission. Now there is Lyman alpha
In here as well, the Lyman, but you can't really see it because it's in the ultraviolet. But there's this purple glow largely comes from the combination of the visible greenish red Balmer series and then the Lyman lines near the blue side of the visible. It gets this nice purple glow. Okay, so anyway, this is literally it for classical hydrogen, right? This is all you see back in the old days. Not much else to talk about. All right, we have a formula that perfectly defines exactly where every energy level is to very, very high precision. We know the hydrogen atom exactly, very simple formula. All right, we basically completed the spectroscopy of hydrogen as far as we can tell. Now, where are we right now? Well, we're kind of in the time around the turn of the century, 19th century, into the 20th. Quantum mechanics hasn't been invented yet, but optics and the telescopes, optics, diffraction gratings, ways to manipulate light, increasingly becoming more and more precise.
And so in the early 1915s,
Early 1920s, we got to the point where we can start digging, we can have enough resolution in our spectrometers in the visible and the ultraviolet to really start to resolve maybe any fine structure in the peaks that may be there. Right? As far as Lyman and Balmer and Paschen are concerned, each one of these absorptions or emissions is a nice line in your spectrum. Maybe it's got some width. The width is not important here, but each one is a separate line at a different frequency. But that's because the resolution of their instrument, that's the best they can get. So the question is, you can really zoom in on a single spectroscopic transition, say the Lyman alpha line. Is there 2 lines there, 3 lines, 4 lines? Is there any complexity? Of course, there's nothing from our theory to suggest that there's anything different. When we solved the Schrodinger equation for the hydrogen atom, we got an exact answer. Theory gives us precision to 6 or 7, 8 significant digits, no problem. Are we complete? Well, 1920s, we had a new generation of spectrometers that were much better. And so people started again looking back at the Lyman progression and other progressions as well. And I want to focus on this line in particular, the Lyman alpha line, the classic N equals 1, N equals 2, the fundamental transition of hydrogen with helium. And so Lyman just sees one line, right? He just sees an absorption line in his little diffraction gradient in his prism output. It's a little absorption or emission. But maybe we can do our prism even more finely, that we can chop up the light and even more fine gradation than just say plus or minus 1 angstrom. Right? What if we can do it to 1/100th of an angstrom instead? We can see if these lines are a little more complicated than they look on the spectrum. So that happened about 1920, around the time that we started to understand the hydrogen atom in the way that we're talking about it right now. Right here, by the way, this is what the Balmer series looks like. These are the actual colors of the emission. This is where that purple comes from. The Balmer, the 2 to 3 transition, the Balmer alpha line, as we call it. Beautiful red. The next one's blue, and you get a combination, you get a nice purple. So that's just where that purple glow comes from. Right, and so people went back and looked at the Lyman alpha line in detail. And what they find is that the line is actually split into a doublet. Now there are actually 2 transitions deep inside of this line. All right, so here's a different, these are on different scales, but here's a line of the reconstructed spectrum of the Lyman alpha line. And you can see that it's actually a doublet, and it's got an intensity difference, a slight intensity difference, about a factor of 2 or so. I think it's technically a factor of, I gotta think about it. It might be a factor of 2. All right, and so what does this mean? Well, this means that there's a transition between 2 states, 2 final states instead of 1 final state. Right? If everything starts at N equals 1, we're either going to end up in a state that gives you this line or a state that gives you this line. Right? So that kind of suggests that the N equals 2 lines actually have 2 states. There's 2 lines there, 2 transitions, 2 energy levels, not 1. Right? And in fact, you go through all of the lines, you go through the Balmer lines, you go through every single line in the hydrogen atom, and you see this kind of splitting. The lines are split by something that isn't N, right? Something else is coming in to causing some splitting to these energy levels. There's some complication. Right? And I want to explore this today because it's super important. And we're going to realize that, again, what we learned in Gen Chem isn't always correct. It's just an approximation, right? Gen Chem tells us that all the orbitals in hydrogen have the same energies for N, right? I just showed you that. That's what the Schrodinger equation tells us. There's nothing wrong with that. But immediately, the moment I get a good experiment, I can tell you there's something wrong with my approximation. There's twice as many lines, twice as many energy levels at N equals 2 than there is than we expect. There's 2 instead of 1. So of course the question is, where does this come from? Now, one thing that's important to note, it's kind of hard to tell on this axis, it's hard to read. The spacing between these lines is very, very narrow. So these N equal 2 states, the ones that split into 2, they have to be really, really close together. Right? They have to be so close together that Paschen and Balmer and Lyman, they never noticed it. They didn't have the experiment to do it, precision. They're very close together, but there's something that's splitting the N equals 2 line. And this is where spin comes in, right? The only thing we haven't considered in a hydrogen atom is spin. And what we're going to find is that the spin of the electron, when we combine it with the angular momentum of the electron around the proton, causes this splitting. The line, because of spin, doubles into a double. But let's look at that a little bit today. Before I do that, yeah, good, we have plenty of time. I want to introduce some new notation for you. And let me show you why I want to introduce this notation, and it'll become clear by the end of the lecture that why we need it. So let me show you an example. Let's go into, I'm just going to do a quick digression. And I want to go into NIST webbook, okay? I'm going to type in Just really simple. Energy levels of hydrogen NIST into Google. And here we go. Energy levels of neutral hydrogen. Okay. And so they give it to us in wave numbers, but these are all the lines, these are all the energy levels that I wrote down in the energy level structure. They're just defined here. And so here's the 1s state, right? This is the electron n equals 1. And let's look at some of the terms we have here. Let me zoom in a bit for the people in the back, actually. Okay. So here's the energy of that state. Again, this does things in more of a spectroscopic way. They set the ground state to be 0. It says that the 1s state is at 0 wave numbers, as we expect. But let's go to the 2p state and the 2s state. Right, we're going to put that electron in the 2s or the 2p orbital. Well, let's do the 2s first. It's got some energy. Right? And then let's look at the 2p. Right, the 2p, as I said, should have the same energy as the 2s. Right, so what I should see here is this line repeated. But I don't. Instead, I see a doublet, right, that has this term symbol and this J value. We'll have to talk about these two things in a second. What do these mean? And it gives me a doublet. So when I go from the 1s to the 2p state, right, I excite my atom from 1s to 2p. That's like Lyman alpha. I see a doublet. Not only do I see a doublet, there's another line here corresponding to the 2s state. In that transition, right? So there should technically be 3 lines, maybe. We'll have to evaluate that, right? So maybe it's a triplet. Of course, I just spent the last 30 minutes saying all the n equals 2 states are the exact same energy, regardless of what orbital you're in. But it shows me that there is, when I put it in the 2p, there's 2 different places to put it, 2 different p energy levels. And there's a separate one of different energy for S. Very strange. So we need to figure out what this means, right? If you learn hydrogen atoms and atoms in CHEM and you want to go, do some spectroscopy, maybe you're doing laser-reduced breakdown spectroscopy of Dr. Marsico, looking for atomic energy levels. You're doing it for hydrogen. Not sure why you would want to do that in forensic science, because everything is hydrogen. But let's just, regardless, you might see a line here, right? But it's a triplet. And you're like, what are these, right? And you're saying, okay, well, this should be around the 1 to 2 transition, the Lyman alpha, but there's 3 lines here, and they have these weird labels, right? CHEM doesn't teach you how to interpret these labels. Right? And I can go to any atom I want. And we'll look at some next class when we talk about multi-electron. But you'll see these term symbols and these J numbers for all the states, right? So what does that say? Well, it says that this configuration, right, this is the CHEM approach to hydrogen orbitals and hydrogen energy levels, doesn't work. It's more complicated than that, right? And I just keep going, right? You see the doublets split into 2. The F orbitals, if we really want to excite, are split into 2, right? There's so many different doublets, right? All the little states split. Let's look today about what that is. So what I'm going to do today with some luck is we'll understand this term number and this as well. Okay, so let's see if we can get an understanding for these 2 numbers that we need to understand what exact state we're putting our hydrogen atom in, right? But the hydrogen levels are actually a function of 2 parameters, this term symbol and this J number. It's not just one symbol or one number, N. Okay, so let's look at that today. So I'm going to start with the term symbols. These 2s, 2d, these things. All right, this is just a common notation we use in chemistry for an energy level of an atom. All right, it's perfectly general, and it includes, what it really focuses on is not the n level, because as you can see, there are many states that have the same term symbol, right? These are 2s's, there's 2 that are 2d, but they're in different n's. Right, this term symbol tells you something about the angular momentum of the state. Okay, so we have a number that tells us the n that we're in, which orbit we're in, and then we're going to have this term symbol here that tells us something about the angular minimum of the electron. And then we're also going to find that this also describes something about angular minimum as well. Right, so angular minimum comes in to our understanding of the hydrogen energy levels, all atoms, it just comes in as a much smaller correction. Right? The idea is that when we solve the Schrodinger equation, remember, we've assumed the atom is spherically symmetric. And so at 0th order, if we don't count for spin, we'll see, all of the angular minimum states have the same energy. Doesn't matter, because angular minimum is determined by the orbit. Right? That ultimately the orbit distance, n, determines the energy. All that radial part, all the angular minimum part, that all averages out. Just goes away. But when we include spin, we're going to find that the spin of the electron will affect the angular minimum of the system in such a way it'll change the energy. And the term symbol tells us something about that. And then we're going to have to figure out what this number means as well. All right, so let's talk about term symbols. It's just a notation about the angular minimum of the electron. All right, atomic term symbols. All right, and the reason why I introduce these is because they're a dime a dozen in chemistry. And they're also very useful. Because again, the 4S only tell the notation 4S or 2S only tells us so much. There's much more fine events going on in our hydrogen atom we need to consider. All right, so the notation for this, very simple. There's a big letter in the middle called L. That's the orbital angular minimum of the system. The subscript is J, the total angular minimum. I'll write these down. And the superscript on the back side of the L is 2S plus 1. All right, you should know what these labels are already. L, of course, is the orbital angular minimum. Okay, so, and we use the letter. So L equals 0. We call the S state. L equals 1 is P state, and so on and so forth, right? You know all this. L equals 2 is D. Okay. J, well, let me do S first. S is the spin, total spin of atom, total electronic spin. Let me say that. It's of the electrons. Because the nuclei can also have spin. We're not considering the nuclei here. Okay, so for hydrogen, example, for hydrogen, S is 1/2, right? Because this electron, there's only one electron that has a spin of 1/2. That means 2S plus 1 is 2. We call this a doublet. Doublet. All right, and J, J is really easy. J is L plus S. This is the total angular minimum. So we sum them together. Okay, so let's do some examples. Really, really easy formula once you figure it out. All right, so let's do an example. So let's do hydrogen in its 1s state, right? Let's just start with the 1s state. Hydrogen 1s. Let me write that a little cleaner. All right, that's its ground state, of course. So let's write down our numbers. We have L. L is 0 because we're in S. S is 1/2. Therefore, J is 1/2. Okay. So the way we would write the term symbol for this state is 2S 1/2, just like that. Right? So this specifies everything we want to know about the angular minimum. It tells us how much angular minimum orbitally the system has. tells us something about what's called the spin multiplicity. We'll see this come up later when we talk about multi-electron atoms. Hydrogen only has one electron, so that number is always 2. They'll never change. And the total angular minimum of the system is 0 plus 1/2, 1/2. Super easy. So let's try something a little more complicated. We'll do a couple of examples. Let's do the
2s 1/2.
yeah, 2s 1/2. Let's do 2p. L is equal, sorry, not L is equal to 0. L is equal to 1, right? Because it's a p orbital. S is 1/2. Now, the question, of course, is what is J? Well, J is just going to be the sum of those. It's going to be 3/2. But we're going to come up with an issue here. Is that, remember, spin can either be plus 1/2 or minus 1/2. So when I add L and S together, of course, I get 3/2. But I can also take the difference of L and S, right? I can have the spin. So if L is 1, let's say that means it's moving clockwise around the atom. All right, so the electron is orbiting clockwise around the atom, but the spin is opposite that direction. So the spin is pointing in the opposite direction of the angular momentum. So the net of them will be the difference of the two. Or they could both be orbiting in a clockwise fashion, they add together. Okay, so there's actually an ambiguity here. J can be 2 different numbers. It can also be 1/2. All right, we'll look at this very carefully in just a minute. Just something to consider. So there are 2p term symbols for H. There's the 2p 3/2 and the 2p 1/2 state. Well, here we go, right? We're starting to see that doublet structure start to form, right? The p orbital, there's an ambiguity in the angular momentum of the system. It can be 3/2 or it can be 1/2. We can add the spin and the angular momentum together, or we can add them against each other. They could be working together, or they could be working against each other. And so the 2p state is actually 2 states together. There's one that has 3/2 angular momentum, where the electron is spinning net faster, or it can be 1/2 where it's spinning net slower because the spin is working against the orbit. You can already see that if we make it excitation, we do the Lyman alpha transition, we're taking an electron from this orbital and putting it in this orbital. Right? 1s, 2p. There are 2 of them. And so if the energy is different between these two, we're going to see a doubling, right? Because this energy from this 1/2 to 3/2 is going to be different than the energy from 1/2 to 1/2 by some number. At least that's what we think. This already generates the fact that there's going to be 2 different states. 2p can be in 2 different orientations. And we're going to see they have 2 different energies. Let's just do one more example and then we'll talk about J, right? Remember that when let me just remind you really quickly. On NIST, that we've already discussed these 2 things, right? The 1s state has a 2s term symbol, and J is 1/2. 2p has a 2p term symbol, and J can be either the sum of L and J, or L and S, or the difference of L and S. 1/2 and 3/2. Right? And you can see that as we go down. All right, so we're already starting to understand this qualitatively, why the hydrogen orbitals are kind of funky. And calling things 2p, 3p isn't exactly correct. Because there's actually 2 2p orbitals. One where the spin and the angular momentum are working together, and one where they're fighting against each other. Let's just do one more example. It's a little bit of a spoiler, but I'm just going to show you how easy this math is for term symbols. Let's look at the helium atom and its ground state, right? So what's its ground state? 1s2, right? Right, you got a nice valence shell of 1s electrons. Okay, so let's calculate everything here. What's L? Well, L is going to be the sum of the orbital angular minimum of the two electrons, which is 0 plus 0. They're both s, 0. Okay. The spins, the net spin is going to be spin 1 plus spin 2. Right, and how do electrons add into an orbital? One goes spin up and one goes spin down. So this is 1/2 minus 1/2, which is 0, and J is 0. So this is what we call a 1s0 state, a singlet. Call this a singlet state. Right? Everything where the electrons are paired, right? The ground state of everything where the electrons are paired, you don't have unpaired electrons. We've always are in a state. Right? This is a state, well, a singlet state, 0 net angular minimum. Right? This is a state where the electrons are paired, the spins cancel each other out. There's no net spin, and you're in the S state, right? This is pretty much all the ground states of all the noble atoms, noble gases, have this term symmetry where the electrons are paired. Right? And you can imagine now if we excite one of those electrons, we could even flip the spin. We could make them both spin up if we put one of the electrons in another state. We'll look at that next class. Okay, really, really easy math, right? You just add for each of the electrons in your atom, you add their angular momenta together from the electron configuration. Think about their spins, how they pair together. Remember, every orbital, 2 electrons can go in, one spin up, one spin down. And then you just add everything together and you get this lovely term symbol. All right, and let's just convince ourselves really quickly that this is correct. So let's go to the energy levels of helium. Right, and the term symbol is 1s. We'll have to consider the next one, which is very interesting, where you excite one of the electrons into the 2s orbital. This is with the 1s, 2s configuration. See that this is a triplet, which is interesting. We'll have to look at that next class. This is where the spins actually add together, right? The total J is 1. But there's no angular momentum in this orbital angular momentum because it's s. It's in the s orbital. So this is entirely spin 1/2 plus 1/2. So this state is where you've taken one of the electrons in your helium atom, flipped its spin to be the same as the other one, and you have these two in separate states. And as you can see, interestingly, the equivalent state is where you take one of those electrons in a 1s, but you don't flip the spin. So they're both, say, spin down or spin up. J is 0 there because they cancel each other out. That's actually higher energy. Very interesting. You would figure that it's nice to have your electrons spin paired, right? Spin up and spin down. That's what we learn about the ground state. But when you move electrons into separate orbitals, they actually would rather be the same spin. Very interesting is that. The trip, the state where the spins are matched is more stable than when they're mismatched, or the other way around. All right, so we'll have to look at that next class. It's interesting. But you can see that these things are entirely general, right? I'm building up this general model that I can use for any atom I want. Right? As long as I know, if I know N, I know something about the angular momentum and the spin, J and my term symbol, I can calculate, at least I have some way to talk, very precise way to talk about energy levels. Now, calculating these things is trickier, right? If I ask you what's the energy of the 3s state for helium, 1s, 2s, 3s state for helium, ask you to calculate this number, that's a very hard thing to do. But at the very least, you now have a formulation, a way to talk about what the structure of this state looks like, right? Maybe not the energy quantitatively, but qualitatively, you understand what the electrons look like when you look at the term symbol. Okay. So what I want to do is talk very briefly, and we'll talk a little bit more about this next class too, is about how the spin affect angular minimum, right? We have this J term where we're adding the spin and the angular minimum together, right? And the net angular minimum of the system is dependent on these two values. So how does that math work? So I want to go back to thinking about vectors, about angular minimum again. We'll call it, and so this term where the spin adds or subtracts to the orbital angular minimum, there's a very specific term for it. It's called spin orbit coupling. Now, spin orbit coupling is somewhat of an advanced topic, but it has very, very deep impacts. There are effects of spin orbit coupling semiconductors, spin orbit coupling in rare atoms, magnetic materials. Spin orbit couplings are found to affect the chemistry in biological systems. The concept of phosphorescence, right? If you've ever, like a glow stick, you give the glow stick some mechanical energy, you excite it into this state that's long lasting and it just glows for a long time. The ability to get something into a state that's phosphorescent requires spin orbit coupling. So spin orbit coupling is one of the ways and most common ways that atoms and molecules break the rules. Because spin breaks the rules. The way that we build our models is just with orbit, right? We build up the hydrogen atom just considering orbits. We didn't consider spin. So when spin comes in, spin's kind of a dirty little hooligan sometimes. And it will affect the angular minimum and mess up your energy levels and do even more complicated things. Spin is very, very important in all of chemistry for this reason. It allows, often spin will allow you to do things you're otherwise not allowed to do in chemistry. Pretty much anytime we ever talk about something being forbidden or allowed in chemistry, there are exceptions. Spin can break them. Include spin, and your spin is sufficiently fast enough, your electrons have that angular minimum intrinsically, there's enough of it, you can do all sorts of crazy things that you otherwise would not be allowed to do in chemistry. So let's just work out very simply how this works for hydrogen. All right, so we're going to set the problem up with vectors. All right, so the first vector we're going to use is L. All right, so the electron and H, the H atom, has orbital momentum. I'm going to call it orbital ang mom for moment of momentum. L, which is a vector. All right, it has magnitude h bar squared LL plus 1 square root. All right, the electron also has spin angular minimum S. Sorry, that's not supposed to be a hat. That's supposed to be a vector. We have S and L, which can only have two magnitudes. So the length of S can only be plus or minus 1/2 h bar. Okay, so what we're going to do is define the total angular minimum. Now what we'll do is define J as equal to the sum of the L plus S vectors. Okay, so let's think about what that does. All right, so let me just kind of very generally write an example. So we're going to do a very, very simple vectorial picture. So let's say L is in this direction. All right, and we set L equal 2. All right, so we have an angular minimum vector that has length. Well, L equals 2, that's 2 times 3 square root of 6 h bar. And then what we're going to do is we're going to add, let me draw 2 of them. I'll show you why in a second. L equals 2. So we have, yeah, square root of 6 h bar. So we have 2 L equals 2 vectors, and S can either be add positively, so in the same direction as L, plus 1/2 h bar, or in the negative direction, minus 1/2 h bar. Right? So there are 2 ways to add these vectors. Right? We could add the S 1/2 vector in this direction. So, and again, I'm arranging them tip to tail like you do in any old vector class. Right? And we end up getting a net vector, J, which lies along this trajectory. And what is the total angular minimum of J? Well, it's going to be the sum of the 2 vectors. It's going to be 2 plus 1/2. Right? So that's 4 over 2 plus 1/2. J is 5/2 here. All right, we've added the 2 vectors together. The spin is working in conjunction with the orbit. So the net angular minimum of the electron is faster because the spin's pushing it along the orbital trajectory. Right, but there's an equal way to do this, right? We can instead subtract S. So the spin is minus 1/2 instead. And then J is going to be the difference of the 2, which is 3/2. Okay, so depending on how we add the electron, the spin of the electron, we get 2 different angular minimum states. And in fact, there's a beautiful rule that we can define. We can add as many angular minimum we like, but there's a really nice rule for addition. If you add 2 angular minimum vectors, L1 and L2, so these are angular minimum vectors. I got to be very careful about that. They're not any old vector, but angular minimum ones. Adding 2 vectors L1 and L2. So for instance, spin or orbital, it doesn't matter. Then J, the total value, can take on any value between the difference of the angular minimum Note that I wrote the absolute value. You can't have negative angular minimum. You can only have positive, net positive. So it has to be the absolute value. We can add 1, and then we can just keep increasing this by 1 until we get to L1 plus L2 minus 1, and then L1 plus L2. Okay, so this is a really easy example because spin only has 2 projections. Right, but imagine if the spin that you're adding is, say, for instance, 2 electrons. Right, you have 2 electrons in your atom that are fine. They can each have electron or angular minimum of either plus 1/2 or minus 1/2. Right, so there's going to be a combination where the total spin is 1. But there's also going to be a combination where the spin is 0. There's gonna be a combination where the spin is -1. And then when we take those combinations of spin, we gotta add it to the angular minimum of the vectors, right? There's all these different additional terms that you have to keep adding. You gotta keep adding, right? We combine the spins together, and then we combine them with the orbital angular minimum of the electrons, which we then combine together with this rule, right? You can just build up these series of sums of states. And then finally you get a J where all of them come together. And so on the homework, I play around with this quite a bit. Pretty much every problem on the homework right now is about playing around with these numbers. And it's all about spins. Once you figure out the additions of how spin combines with angular minimum and stuff, you can learn so much about atoms and molecules. It tells you pretty much, right? If you know N, the only thing you need left to know exactly about the state of your system is the angular minimum properties. And so you find out that you learn a lot about the structure of atoms by thinking about how angular minimum atoms interact. Now, I'm not going to go into any more details because I'm out of time, but we'll come back to this on Thursday and we'll do tons of examples. Okay, we'll look at bigger atoms, multi-electron atoms. We'll see how these things trend. And we'll also think about the splitting between the different levels as well. All right. Have a good one, guys. Send me an email if you want to know your exam grade. Otherwise, I'll have them posted tomorrow morning.
Just real quickly, so.
Yes, sir.
for The angle of the OS and degree, OSO angle, this is in regard to the,
Mhm.
it should be like 114 degrees.
It's about 120, so that's pretty reasonable.
Okay, and
Yeah,
then
that's
just,
reasonable.
and then the plot that I need to attach is just this graph?
Yeah.
All right. And then and for the comparing, I just need to say how off it is, like a percent error?
Yes.
Okay,
Yeah, and maybe think about what your uncertainty in that is too.
all right. Yeah, so it's like 122.4 is like the literature value.
Yeah, that sounds right to me.
Yeah, because I'm just looking at the data analysis sheet. So I don't have to watch the beginning of what it is.
I'll let you know who comes to upstairs.
Okay, very good.
I'll see you
I
tomorrow
don't have
for-
solutions for you, but
I can do the spin questions just fine, I know that.
yeah,
And I know that's problem one, so
Yeah,
it's only the hour-long session, so it'll probably take a couple hours.
yeah, okay, yeah, that's fine.
Don't worry about it,
All right.
and I'll see you tomorrow to just trying to figure shit out when the breaks start coming.
Yeah, I'll be around. I have to go to Wesleyan in the morning,
Yeah, I mean,
so I'll be around hopefully about 11 or 12.
yeah, I'll be good after research methods.
Okay.
I basically finished our,
Okay,
or go homework already, so.
thank you.
Am I still need to find some research tomorrow?
Yes.
Okay.
Um,
You said, okay, 11, around.
so I won't be there till noon.
Okay.
So anytime after 12 will be fine.
Okay, that's good.
What's up, homie?
I'm just waiting for you to go to Abby's class.
Oh, yeah, that's right. Yeah, hold on a second.